Today I'll be talking about transforming DNA evidence into reliable information, computers, science, and society. So let's begin. In 2009, the National Academy of Sciences issued a report, Strengthening Forensic Science, in which they said there was really no basis to much of forensic science and a lot more was needed. They spared DNA and they said, oh, DNA is fine, focusing mainly on simple DNA that's from one person. But the question was opened, where is the science in forensic science? And so let me begin with the genotype. This is the main concept in forensics, and that is we have a genotype from our DNA. Forensic scientists will look at about 15 different locations that are short tandem repeats, and these are length variations. So a particular allele at a location may have up to 15 different length variants. Scientists measure the length on a sequencer of the fragments, and then a pair of these alleles is what you inherit. One copy from your mother, one copy from your father. And genotypes are important for two main reasons besides identity. One is because they come in pairs, there's a lot of variation. If you have about 15 alleles, then 15 squared over 2 is roughly 100. So at each location, each of these tests, in a multiplex test, you're getting about 100 different possibilities, of which a person has one. And that means 100 to the 15th is a big number. That's a lot more genotypes than there are people. The other factor is that there's a pair of genotypes. And so when signal analysis is done, we know to look for either two copies of one genotype, a homozygote, or a heterozygote, which is a balanced pair from each cell. And interpreting DNA is pretty simple with these genotypes if you have one person. You take a cheek swab or a pool of blood, and you have DNA from one person as indicated on the left. The laboratory extracts the DNA, and then they amplify it with polymerase chain reaction, making many millions or billions of labeled copies at each genetic locus, each of these locations on a different chromosome. And then the data that we see in the center is very simple. There's either one or two large peaks corresponding to the heterozygote or homozygote genotype that you have, the pair of alleles. In this example, based on size, the scale of the number of repeats, the allele would go 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and so on. Here we see two large peaks, one at 10, one at 12. There's nothing anyplace else. So the interpretation is very simple with single source DNA. Looking at the data rules out the other 99 possibilities, and you're left with the one possibility supported by the data, which is a 10-12. And that's shown on the top right. That's the evidence genotype. That can be done objectively. There's really no issue in interpreting that data, and afterwards a comparison can be made to determine whether or not there's a match and the strength of that match, which is the match statistic. Formally, it's a likelihood ratio. So as you maybe came in through the Fort Pitt tunnels and has been wandering around the city, you've seen the Pittsburgh skyline. And it's a nice skyline, but what's important for this presentation is that it's a complex pattern. There are highs, there are lows, there's features of those highs and lows, like the crenellated top of the PPG glass building. And when we see data, we tend to look at the entire pattern. But in forensic science, that hasn't been the case, and instead scientists will draw a threshold across the tops of these peaks, these data peaks or the buildings, in order to simplify the data, to reduce combinatorial possibilities, use simple formulas, and basically be able to do it by eye without having to use a computer. And the result of drawing a threshold is that the buildings or the data peaks are reduced to all or none events. Either a building is present, shown in blue, or there's a vacant lot. That's not actually what the skyline looks like, but it's certainly much easier data to explain. And there are some issues with that. For example, if you look at the building event all the way on the left, its building is just a little bit over the threshold. Whereas if you look at the building that's just missed all the way on the right, it's just under the threshold. Threshold-based methods would say the building on the right doesn't exist. It's a vacant lot. But we know it's not a vacant lot because we can see it. So issues arise with DNA mixtures. Almost all DNA evidence nowadays is a mixture of two or more people. From sexual assaults, handguns, surfaces, touch DNA, most evidence is mixtures. And with mixtures, you don't just have one tall peak or two tall peaks. You have a complex pattern that looks a lot more like the Pittsburgh skyline. And so that can be difficult to interpret simply. So what forensic scientists started doing 15 years ago was to simplify the data, to simplify the interpretation. If you just draw a threshold and ask what's over, what's under, and approximate the data by saying, well, if it's over the threshold, it's real. If it's under the threshold, it's not real. You end up with a very simple rule for calculating match statistics. And here are the steps. Step 1, apply the thresholds to the peaks and hope you get the right alleles that are genetically present. Step 2, add together the frequencies, the prevalence of these alleles in the population. Then square the number, the sum, take the reciprocal, and you now have at one location corresponding to this data, the probability of inclusion, or PI. If you have a multi-locus test, say 15 different locations in one tube, multiply these numbers together, and you end up with a combined probability of inclusion, the CPI match statistic. And that's been the basis of forensics and mixture interpretation for over 15 years. Very simple rule, and it's used to analyze mixtures and determine a match statistic to help police, and ultimately mainly used to help convict people in court. But there are problems with it, because as you can imagine, if your starting point is throwing out your data, there might be an issue. And there were issues, and they were known very early on. In 2005, the Department of Commerce in NIST, which is the National Institute of Standards and Technologies, did a study where they sent out a very simple two-person mixture to 69 participating laboratories. Most of them said the mixture was uninterpretable. Of the groups that replied with a match statistic, the match statistic ranged from 10 to the 4th, tens of thousands, to 10 to the 14th, which is hundreds of trillions. So there was really not much reproducibility in this study. Most scientists said there was no information there. If people said there was information, the numbers were all over the map. 10 orders of magnitude is not exactly high precision. There was also an issue of bias. The bias arises in several ways, but on the left we see the first step is an analyst chooses their data. They pick which of the tests, which loci they're going to use and which they're not going to use. The thresholds help them determine which data peaks they're going to use, which data peaks they're not going to use. They're not going to use the patterns or the heights of the peaks, but they begin by choosing their data. And then, at the same time or afterwards, as shown in the middle, they then decide whether the defendant is present or not present in the mixture data. So that's a human subjective decision that may again help adjust the data. After you've chosen the data and made the decision of whether or not the person's present, then you say, let me calculate an inclusion statistic. These inclusion statistics actually only work if the person's included. So they're a way of confirming an analyst's impression of guilt. In much of science, we don't do steps 1 or 2. We go right to step 3. We put the data into a computer and it calculates statistics for us. And that's what we rely on. But in forensic science, that isn't what happens. And the result is that people are put into the process, and it's to overcome limitations of very simple software, and human bias is introduced. And so workers wrote papers about this type of problem when bias was seen, with mixture interpretation. And then NIST did another study in 2013 where they asked if a second threshold was introduced, which is recommended by the FBI. One threshold didn't work, so the question was, what if we use 2 thresholds? And in science, we often account for statistical variation with probability equations, modeling, and so on. In forensics, what was done at the suggestion of the FBI was to introduce a second threshold. They called it a stochastic threshold, which meant if they saw too much variation, they wouldn't use the data. And the idea of this was to help eliminate false positives, false identifications. What happened in the study is on one of the samples, which was a 3-person mixture, out of 100 labs that responded, 70 falsely included somebody who wasn't present and then reported a match statistic based on that false inclusion. Only 6 groups correctly excluded the person. So there were well-known problems with these methods. They became so well-known that 2 years ago, crime labs began shutting down. The Washington, D.C. lab was shut down, eventually taken over by the FBI, who introduced other threshold methods. The concept was they weren't using the threshold methods properly. And then in Texas, at some point it was realized that about 25,000 mixture samples had been interpreted using other threshold methods that weren't the current threshold methods. But the question arises, do these threshold methods work at all? Does the combined probability of inclusion as the statistic even make any sense? And toward that end, I looked at some data from crime labs and tried to understand what was the scientific basis for this method. There was no mathematical basis that made any sense. This is a paper that was published in the Journal of Pathology Informatics in 2015. And the title of the paper is Inclusion Probability for DNA Mixtures is a subjective, one-sided match statistic unrelated to identification information. So how did we arrive at that conclusion? We took data from a laboratory as part of a validation study and looked at it locus by locus. So instead of looking at the aggregate statistic, which are numbers like millions or billions or trillions, from looking at the product of all 15 locations, we broke it down to one locus at a time. The aggregate statistic was interesting in that the number in other studies we had done with other labs was always around 1 million. That was really puzzling. If you have information that we know can range from a match statistic of 1 up to 1 trillion trillion, that is a log of 0 to a log of 24, and exclusionarily goes the other way when you're excluding someone out to a log of negative 24, 1 over 1 trillion trillion. Why is it that if on the top, using computers and statistical modeling, we're seeing a broad range in study after study of match statistics, on the bottom slide, what we're seeing is that the reported match statistics with 13 or 14 locations in one test was always around a log of 6. How do you always get a log of 6? What are you measuring if the information is ranging between 1 and 1 trillion trillion and your number is always around 1 million? So that puzzled us. And by fractionating these tests and looking at all the locus tests individually, not as part of each sample, we looked at some data. So this is on a log scale, and the scale goes out to basically 0, 1, and 2 correspond to match statistics of 1, 10, and 100 on a log scale. There is no left side because the numbers are only inclusionary. The inclusion methods can't exclude. But if you symmetrize it, you can see what the bell curve would look like. And what we noticed was that the average of this one-sided truncated distribution was 0. It was a normal distribution if you filled in the left. The average, meaning average information, was 0. And it looked as if all that was happening was that people were taking the right tail, sampling from the right tail of a distribution whose average was 0 information. I'll comment that if you just look at the white part, the positive observed data, that the average of the truncated normal is about half a log unit. We'll come back to that. The next thing that we saw was that when we compared it with a tested, validated system that actually measures information, has been proven to measure information, those match statistics are shown on the x-axis, and the positive values from these locus probability of inclusions are shown on the y-axis. On this log-log scale, if the inclusion method on the y-axis actually was the same information as the x-axis, then all of those 500 plus points would have lined up on the y equals x line, 45 degrees. But they don't. The ones below the line are giving less information. The ones above the line are giving more information that's actually present, and the ones to the left are just making up information that isn't there at all. And in fact, the r squared was less than 0.2. So there's essentially no correlation of the main match statistic that's been used in hundreds of thousands or millions of criminal cases with actual identification information. And if you read the paper, you'll see that the conclusion is that this prevalent inclusion method used in criminal justice is just a random counting procedure. And we're trying to explain why we always get the number of 1 million with about 12 tests, and this is why. First, it's a one-sided match statistic, as we saw. It's a truncated normal distribution. We're just seeing a distribution of positive log LR values, and it's positive and centered at 0. There's no information on average. But sampling from the right tail, we can see values at each locus that are uncorrelated with identification information. And fifth, the inclusion distribution has a positive mean of around 0.5. So, by the law of large numbers, if an analyst chooses to report 12 tests, and each test has a log match statistic of 1/2, then 12 times 1/2 is 6. 6 log units is 1 million. And so just by counting up, using a sophisticated random procedure, counting up how many tests and analysts thought a person or a defendant was included in the data will give that match statistic of around 1 million consistently. It has nothing to do with identification information, but it's a way of putting a number to an analyst's subjective impression. A better way of doing this, which many groups have done, we started at Cybergenetics here in Pittsburgh in 1999 on this, is to begin with the premise of use all the data. Don't use thresholds. Don't simplify. If you're going to use all the data and try to explain all the data, you're trying to explain and infer all the genotypes that are present, the amounts of the genotypes, known artifacts like PCR stutter or imbalance. If you're going to understand the variation of the data and the variation of your model in explaining the data, you're going to need a robust Bayesian model. Should have about 100 variables in a typical mixture problem to solve a DNA mixture. And what the DNA mixture problem becomes is separating out the genotypes that are present in the data. So if there's 3 contributors in a mixture, the computer will separate out 3 different genotypes at each location. The uncertainty in the genotype in the model will be represented with probability, and there'll be lots of variances as variables all over the place to help explain the experiment. That's modern science for the last 25 years, is Bayesian modeling of all the data, solving these high-dimensional problems with Markov chain Monte Carlo. Okay, so that's what TrueAllele is. And it's been used in casework for almost 10 years. There have been 34 validation studies, 7 of them published in peer-reviewed journals. The workflow removes human bias. Nobody chooses data or tests. Whatever it is, it is. It's been used in most states in the US. The math has been published and disclosed. And it's very neutral. Unlike the inclusion methods, it can exclude or include. You can get a match statistic of 1 in a million that's exclusionary, as well as a match statistic of 1 million, which is inclusionary. As you can imagine, on a complex mixture, almost everybody in the world's excluded from this, except for the few genotypes that might be present. So that can be helpful. Let me tell you about a case here in Pittsburgh. This was a double homicide in Friendship, which is a neighborhood just north of East Liberty. 2 sisters come in from Iowa. One was a child psychologist. The other one actually worked in my neighborhood in Squirrel Hill. And they were killed in a very senseless shooting. Nobody understood what it was. They were shot in the back of the head in their home that they had moved into recently. There were many items of evidence, and most of these were mixtures. There was DNA under the victim's fingernails as they fought back and struggled. There was DNA left on cups or hats. There was a car that was driven where there was DNA found in the car, or socks that somebody may have worn on their hand. And these were all low-level mixtures, 2, 3, 4 contributors. And our local crime lab did what most crime labs would do, which is they applied thresholds, they threw out most of the information, and they couldn't interpret the data. The words shown in red is language from the reports. The hat, they could reach no conclusions. The cup, it was insufficient. Cannot be excluded. Insufficient data, too complex, no conclusions. This is what happens with most of the DNA evidence in the US right now, and actually around the world. It's just thrown out. At some point, the district attorney's office asked us to get involved. We've done a number of cases with them. And we were able to put reliable match statistics to most of the evidence items. On the identical data, the same electropharogram data, the lab could report 5 match statistics that were inclusionary. Probably not that accurate, but they could report something. And the TrueAllele computer system, a Bayesian modeling system that used all the data, was able to report 17 matches. These matches were presented at trial, and there was very little question that Alan Wade, the defendant, had left a trail of evidence as he went from place to place across different crime scenes. And he was convicted and found guilty on all counts in the slaying of the East Liberty sisters. There's another fact that's worth noting that I learned about afterwards. And that was 6 weeks before the double homicide, there was a burglary of the sisters' home, and a hat was left. It's actually a knit cap that was left. The police didn't bother submitting it because the crime lab really didn't process complex mixtures from hats. Nowadays, they submit them after this case, but they still don't find anything. And we had a chance to look at this hat as part of the evidence. When the crime lab looked at it in this case, they found no information. But we actually found a match statistic to Alan Wade of around 65,000. And since he was present in a DNA database, he could have been identified, but he wasn't. But if you can apprehend criminals before they commit crimes based on the burglaries that they commit, then you may not have to go 6 weeks later for the double homicide. So I often view forensic DNA more as a field of potential public health and preventative medicine if it could be done right. In Allegheny County, we've done almost 60 cases. There have been 13 trials. 12 of them have been for prosecutors. A few weeks ago, I actually testified about DNA evidence that the prosecutor had given to the defense. It was another double homicide, and the question was this a struggle or was this intent? So there was no question that the defendant shot the 2 individuals. The question was, by analyzing all the DNA, would that help in understanding to what extent there was self-defense versus an intentional homicide? And actually, the individual was acquitted, based more on the 911 call than on the DNA. So what you can also see is that in addition to there being 4 exonerations, by which I mean acquittals, drop charges, and so on, because the TrueAllele can exclude people statistically in ways that simpler crime lab methods can't. If you look at the column on outcome, what you'll see is that most of the outcomes are guilty pleas. Why? Because the DNA is back in the case. If the lab can't interpret the evidence, it can be collected, it can be processed, a lot of things can happen. But if it's not interpreted properly, then it never makes it into a criminal case. Once it's back in play as evidence, then it can be used to help get a resolution, which can be an acquittal or a guilty plea without having to go to trial. There's even been in some cases on a complex handgun where both things happened. One person had the charges dropped against them, the other person pled guilty because the DNA could show who was present and who wasn't present. TrueAllele has also been used for exonerations. We had our first major exoneration a year ago. 2 people were involved, 2 defendants. This was a case where about 1989 in northern Indiana. There was a gang of 5 men roaming around in a car, and they were committing crimes. They were called bump and rob. So they'd bump somebody's car, the victim would get out, then they'd rob them. Then they became bump and beatings, and then they turned into bump and rapes, or bump and rob and rape and beat. It was getting out of hand. So the police were working very hard to find people, and Darryl Pinkins and 2 of his co-workers had left their factory. Their car broke down on a cold night. They left their uniforms in the car. Their car was broken into. The uniforms were stolen, presumably by the same gang committing the crimes, and then they left the uniforms at the crime scene. And on the basis of that, 2 of them, Darryl Pinkins and Roosevelt Glenn, were convicted. 15 years ago, the Innocence Project in Indiana, the wrongful conviction clinic, developed DNA data. And it was mixtures from the victim's jacket and from her sweater. They were able to determine at the time, using threshold methods, that there were 2 major contributors, like 80-90% to the mixture. And the appeals court for post-conviction concluded that if there's 5 assailants and there's 2 potentially exculpatory DNA profiles with 3 accused or defendants, 2 + 3 = 5, so 2 men stayed in jail for this, Pinkins and Glenn. We looked at the data with TrueAllele, which uses all the data and has a Bayesian model and so on, and we were able to find a lot of things in the data. I'm not going to tell you all about them, but essentially doing what you can do with computers and statistics, joint interpretation of all the data instead of single samples, identifying minor contributors, 5% components, exclusionary match statistics, as well as showing statistically that 3 of the perpetrators were brothers. And that was not the case of any of the defendants. And so about a year ago, Darryl Pinkins, who was still in jail, was freed from prison. So good technology can help with innocence as well as with guilt. Here are some suggestions for science, and they would be to open DNA to public scrutiny. We know the crime labs have failed on hundreds of thousands of mixtures. Why should government labs using failed techniques have a monopoly on interpreting DNA evidence? The DNA mixture cases must be revisited. We know the answers are wrong, and there's a lot of potentially exculpatory evidence in there. There's a lot of education that's needed for trial attorneys and judges. I and others work on that a lot. Mixture interpretation should be fully automated using rich statistical models that get people out of the process and eliminate subjective bias. The methods should be extensively validated and shown to work, kept within their limits, and what the labs say works well for them often historically has not been what the best science is. Actually, toward that end, we recently here in Pittsburgh started a nonprofit organization, Justice Through Science, whose mission is to reanalyze all of this forgotten DNA evidence pro bono for free, as well as to educate lawyers, scientists, and society. There's more information on our website about the technology and how it's used. Thank you very much.